So again, a hyperspectral study. I'm going to present to you how I identified vertically zoned alteration footprint above a sediment-hosted base metal deposit that is situated undercover and was previously thought to be geochemically and always blind to any kind of surface or other alteration. I'm going to show you how I did the processing for the hyperspectral data, how I validated it using microchemical methods, and then how this information is valuable in kind of regional scale prospecting using remote sensing data sets. This is part of my PhD study, which I finished about a year ago with the help of Sandy Okipinti, Karsten Laukamp, and Marco Fiorentini. It's also published in Our Geology Reviews about a couple months ago. Without further ado, that's where Abra is. It's in the eastern part of the Edmund Basin, in the eastern part also of the quartz crustal scale Lions River quartzite well fault. And it formed during the Mesoproterozoic extension about 1.59 billion years ago, give or take. It's situated in interface of Edmund Group Depositional Package 1 and 3. And that's, however, there's a little bit of a different opinions there. The underlying irregular formation sediments are mostly kind of a deeper platform carbonaceous siltstones, and the overlying Kiangi Creek Formation eroding the irregular formation has mostly siliciclastic composition, is more coarse-grained and everything like that. This figure, I took it from the Galena mining website, same as the recent photos showing the ore. They are working on full speed right now. Nothing was happening when I was doing the study, but now there's a lot of action going on and should be starting off excavation later this year. So it's kind of vertically zoned metallogenic element distribution as well. So sub-economic copper and gold are in the bottom part of the feeder zone. A lot of the lead and silver are in the hydrothermal veins in the kind of upper part of the feeder zone, and then lead and silver, which are the main commodities, are in the stratiform top, which is situated about 300 meters from the surface, and which also has been weathered kind of pervasively to 60 meters depth. The overlying Kiangi Creek the kind of recent academic work before I got into my hyperspectral study were kind of suggesting that Abra, as weird as it is a SEDEX deposit, so sedimentary exhalative, and formed during the deposition of the irregular formation. And therefore, the overlying irregular formation would have eroded away any kind of traces of the deposit, therefore nothing gets to the surface. However, there were a little bit of funny things going on in the drill core data above the deposit. Some alteration could be later, but also the red zone jaspilite alteration in the stratiform part was actually kind of overprinting the lowest formation of the Kiangi Creek lowest part. So, like, what's going on there? So I looked into what's going on between Abra and the surface. One other reason why I was looking to it is because there was abundance of free data. High-logged drill cores 2 kilometers away from the center of the deposit, and so you get the SWIR and the thermal, and I could use those to look into carbonate zonation, which is typical for sediment-hosted deposits, and then other typical chlorite, white mica alteration footprints. I used the AB62 data for validation because it already had a kind of consistent whole rock geochemistry record, and it was least altered, so least messy, so to speak, so I could make kind of an idea some idea what's going on, what's primary and what is later. I did the processing for hyperspectral data. I was validated using SEM-EDS methods and micro-XRF. Repeated the processing for HY2 drill core, other one, and then did all the processing for the 26 field spectrometers, field spectrometer spectra collected from 26 drill holes, 1 per meter. So there's a bit of a difference in resolution, and there's no thermal from those data, but at least we'll get something. Also, Scott Halley had looked into that data and organized the collecting of it, so he was kind of in mind of like there should be something, but he didn't have any geochemistry to compare, and also he didn't have lithology. So I spent a considerable amount of time looking into the lithology, what's the background, what's the kind of framework where I'm comparing the alteration to. Please work. Kind of. Okay, so in summary, this is the conglomerate sequence where the stratiform top of the deposit is. The HY2 is a bit more altered. No. Nice. And here in the AB62, the same horizon is visibly kind of almost unaltered. In AB62, a lot of the sulfidation and the kind of rusty color is constrained into this coarse-grained kind of arcosic sequence in the siltstone of the Erie Gully Formation. I think that's what's it. Now, you've seen all kinds of ways of processing reflectance spectra, from artificial intelligence and then using spectral libraries and different kind of sophisticated algorithms. This is more of artisanal, I guess, approach, using scalars, which are kind of like filters or sieves for the spectra. So I'm using, this is because I had two kinds of reflectance spectra data. I wanted to kind of have a good control that there is no artifacts of using different devices. So first I was using the already mentioned aluminum OH group feature for separating all white micas and kaolinites and all that from other spectra, which was then divided to kaolinite and white mica patches, and using other scalars like for chlorites I could identify also chlorite and white mica patch. And then, like in the white mica only, based on the wavelength position, whether you had a white mica with some iron and magnesium and silica replacing the lattice, or whether it was be more stoichiometric aluminum rich. And then carbonates, I was relying quite a lot on the thermal, and used that then later for calibrating the SWIR processing. I'm going to show you only the thermal because otherwise there will be a lot of figures. So in this plot, you may first made by Green and Shotlock, you see that everything that is in a plot is being filtered by the first feature at 6,500. And then the other two carbonate features, which kind of change place based on the compositional shift in the carbonate, will kind of give the other axis of the plot. In this plot, there are also pure spectral examples of the specific compositions of carbonate, so which I kind of used roughly to color the main composition. These are all kind of mixes, but you need to name them something. Yes, and here it is how it is along the drill hole. We're getting to the more of the validation process now. So this is the most of the conglomerates in strata, which is where Abra, most of the stratiform part is. It contains mostly dolomite, a little bit of iron dolomite, and more anchorite, kind of a composition closer to the most mineralized bit of this core. which has a siderite as a main carbonate phase. And the little black stars show where I have the samples for the SEM-EDS. Come on. Yeah? Oh, yeah. All right. So this is from the conglomerate interval. You can see, or at least there's a first kind of carbonate in matrix, carbonate in a kind of a larger vein associated with the chlorite, which is the blue stuff, and then a very, very tiny later carbonate vein, which can be seen here. So that's the matrix, the vein, and then a later carbonate vein. And these are the EDS point analysis results. Here is more of a stoichiometric dolomite, stoichiometric rhodochrosite, and then more of a siderite composition. And these samples do have more of a close to dolomite composition. However, later phases do show shift towards anchorite and kind of iron-rich composition, which is what the hyperspectral data is showing. This is from and the micro-XRF maps were really good at kind of focusing the work, so I could see in one scan, okay, what kind of carbonates, what kind of micas I would have, and I can target them specifically rather than spending ages in SEM, which can be a little bit tedious. So yeah, back to story. So we have the siderites on blue kind of purplish, and then some less iron-rich carbonate on a yellow, and the black stuff is mostly silica and few feldspars. And here we have, actually there is like a magnesium-rich siderite, which I assume that is the first generation. It's the magnesium-rich kind of a core, which is kind of surrounded by less manganese, more iron, less manganese containing rim. And then there's a third generation which has more of an anchoritic dolomite kind of a composition. So it kind of implies that the later carbonate had less iron, less manganese and iron. And this is from the lowest bed, kind of exhibiting the more unaltered siltstone. It has two kind of carbonate phases, the kind of more of a diagenetic siderite, which is close to a stoichiometric one, or there on the top, and then anchorite, which is later and associated with these nodules in the rock. However, okay, so this is showing, we're moving into the white mica and chlorite. As I said, this drill core is not specific, very altered. However, the sequences from the conglomerate to the most altered lower arcos kind of have this phengitic alteration there in the middle, and still like kind of a message to take from this figure is that some of the white mica in the surface when the weathered sequence are still kind of preserved, although it's evident that the alteration is not extending there. I couldn't find any detrital or primary micas from the overlying units. Most of it is kind of microcrystalline phengitic white mica with chlorite, and usually overprinting some potassium feldspar clasts, so it's clearly seems later kind of a feature. Here we have the data for the HY2, much more altered, and it looks like that the chlorite white mica, phengitic white mica alteration is kind of coinciding with the more of an anchoritic carbonate alteration. Unfortunately, it also looks like that a lot of the carbonates are not really preserved through the weathering in the surface. All right, cool. Which is why I'm moving into the white micas. Here is the final product, or kind of the processing. So I managed to distinguish 9 different kind of mineral assemblages from the SWIR spectra. Thing to kind of focus on is that this is the lithology, which is much more better described the detail how I got into this far in my paper. But this is the conglomerate sequence. This dashed line shows how far the red zone alteration extends, and this line here, or body here, is a sequence of very quartz-rich arkose, which has virtually no other minerals than quartz, or at least that's in the distal areas. However, or visibly, but the alteration that the hyperspectral data shows is, the mineral assemblage is that you have chlorite alteration, chlorite white mica. You still have chlorite white mica alteration that is slightly reduced or affected by the weathering on the surface. So that I took as a sign that it's really the overlying units were there, and this is where was most of the fluids that were seeping through it. About the white mica composition, that's from a distal core. You get more of a short wavelength feature for aluminium OH, and then on the top of the deposit, all of it is more of a phenitic. But the phenitic feature is also kind of affected by weathering. So if you have about 2220 or something, 3215, weathering will shift the aluminium OH feature towards the kind of center, I guess. Ta-da. So, in summary, it is, I don't think it really, based on the evidence, the hyperspectral data from the drill core processing shows it didn't exhale. The overlying units were in place. So it was more of a kind of a replacement style sedimentary deposit. Some people still like to call that SEDEX, but it's really up to you. I find it a little bit confusing. That's why I'm calling it the replacement deposit. And it does have this kind of a typical zoned footprint for other like MBT and VMS style deposits, but also something that is like the white mica and chlorite alteration is kind of similar to that is being seen in felsic volcanic hosted deposit like in New Brunswick. Well, because there's phenitic alteration was preserved to some degree on the surface, and this is kind of proving that my previous work was actually okay. So I collected spectra from the regolith, which showed that some of the white mica kind of had a longer wavelength composition. There was some chlorite also preserved, and this kind of coincides with the kind of anomalously high potassium radiometrics composition, and also longer aster aluminum OH group composition. So this kind of this gives you a coarse kind of idea of how to use the remote sensing data sets, knowing that there is phenitic alteration is preserved on the surface. You can start looking for phenitic alteration, especially in the rocks that shouldn't have white micas in the first place. And I think that's about it. Thank you very much for your time. Hope you made sense of it.